everyone, I'm Victoria, and my talk today is about event-driven systems with Go. We'll talk about implementation, design patterns, potential problems that can arise, and solutions to those problems. A little bit about me. I work as a software engineer at 9. I'm based in Sydney, and originally I'm from Ukraine. I started working with Go around 3.5 years ago, and at the time was transitioning from front end to the back end. And since then, I was building back-end systems, including event-driven systems with Go for media and finance industries. Now, this photo is not what I do for work. It was taken in one of our office tours. That's the only chance we get to sit in this beautiful studio and take cool photos. Otherwise, we're not given any time on TV, unfortunately. And before we dive into event-driven systems, I'd like to thank organizers of this event for making it all happen, 9 for sponsoring GopherCon, and of course, our Gophers, our amazing community. I find it really exciting to be here amongst the people who share the same passion for Go as I do. So thank you for being amazing, and thank you for being here. So let's dive into event-driven systems. There are a few terms that are important to understanding what are event-driven systems. In event-driven systems, we use a synchronous way of communication. And there's difference between synchronous and asynchronous. In synchronous communication, we expect to get a response immediately. So for example, when you have a video call with someone, you start a video call, you say hi, and you get a response immediately. And you expect to get a response. And for comparison, in asynchronous communication, they're more like fire and forget. So an example, an email, when you send an email, you don't expect to get an immediate response. So event-driven systems use a synchronous way of communication. We also use terms messages and events almost interchangeably when we talk about event-driven systems. However, there's a difference we still need to remember. A message is a unit of data. It can be used for different type of communication, including synchronous, for software to communicate. And an event is a specific type of message. It represents a change in state within a system. So while an event is a message, not every message is an event. Event-driven systems are based on a messaging pattern called publish-subscribe. In publish-subscribe pattern, we have publishers. Publishers generate messages and send them out, and they don't know much about who will be receiving these messages, what subscribers are there. And subscribers, on the other hand, they register interest in particular type of events and receive them via intermediary. On this diagram, you can see an event bus. An event bus is an intermediary. It takes events from publishers and routes them to the correct subscribers that are interested in those events. Middleware. When building event-driven systems, we use middleware between applications. There's different types of middleware. It could be message brokers, could be event streaming platforms. They all have different benefits and they're suitable to different projects, but they all share common similarity. They all act as a postal service for computer programs, helping them communicate by receiving, organizing, and delivering messages. So, for example, we have Kafka, Amazon SQS, RabbitMQ, PubSub. They are all can be used as middleware in the ventray system. At 9, we use Kafka in one of our major projects. We use it for its feature to retain history of events. So, for example, when we want to plug in a new subscriber, that subscriber will have access to all the events and will be able to pick up on that. We also use RabbitMQ and probably other middleware as well, depending on the needs of a particular project. So let's take a look at an example of this event-driven system. We can identify that we have a middleware here, which is an event stream, and we have a publisher content API, and on the other hand, we have subscribers, push notification service, and print services. So in this system, we actually have a client and content API that together they form a content management system, or CMS. And subscribers are interested in certain events that happen in that CMS. So let's take, for example, we have an author who wants to publish an article. An author would log in the browser, write an article, click a button, publish, and we will receive that request in the backend in our content API. From that point, we want to write the data we received into the database. In this example, we use Postgres. And also, we want to publish information about this article for other systems, for mobile service that will publish the article to mobile phones of our users. And we also have subscriber print services. Print services will eventually convert this article into a printed edition. And the reason we want to use event-driven system here is because we want to improve responsiveness of the requests that come to content API. So when the user will make request to content API, they will not have to wait for mobile notifications to be pushed or printed edition to be made. That would be ridiculous. So another reason event-driven system is beneficial here is because we can pass the data and, for example, print services, they can maintain their own copy of this data instead of calling content API every time to access articles, so that reduces load on our content API. However, as great as it sounds, there might be potential problem in this system. So this problem is of data integrity, and there's a name for it called dual rights problem. What happens here is when we write content into our Postgres database, then something may go wrong on the way when we try to publish that event. It could be for a variety of reasons. Could be a bug in the code, maybe your application crashed because of bad deployment, or could be network issues. So that will prevent event from being published, and we will not have this data propagated further to print services. So that's something we want to avoid. And I'm definitely guilty of building systems where these things happen, and one day we would wonder, oh, why in one database we have this data and in other we don't have, and we didn't know why. And turns out that some events were just lost and we couldn't even track it. These issues are very difficult to debug. So let's see how we can solve this. We can use a design pattern called transactional outbox that will ensure data integrity in the system. And in this example, we use Postgres, and We are also going to build an event relay with Go. However, you're not required to use Postgres. You can use different databases. I know that, I believe CockroachDB actually provides functionality like this that's much easier to use. But in this example, we use Postgres, and we are going to add a new table, outbox table, which will store events. And we will have to make sure that data is written atomically. What it means is that when we so we either write data in both content table and outbox table, or we don't write it to any of those tables at all. And an event relay in here is going to take events from the outbox table and forward them to the event stream. Now let's take a look at what design patterns we can use for developing our applications. This one is applicable to Content API, since Content API is a part of CMS. It's a very large and very complex application. So in the database, we have a lot of different types of functions that we want to use. So here we have a data access object, which will encapsulate database operations by a particular type. So let's take a look at the start server function. Here we initialize tracing, logging, and establish connection with the database. And then we are going to create a DAO. First, we are going to make an article DAO. Article DAO will contain all the methods for working with article data. And we'll also pass logging and tracing. And the next line after that, we have a media DAO. In media DAO, we are only passing a database and tracing, because we are not going to be using logging. So in this case, we only providing what is necessary for this DAO. So the benefit of DAO is that we can mock it for unit testing easily without having to mock the entire database or having to establish connection with the actual database, which is very convenient. Now let's take a look at a method from article DAO. This method is going to insert article. And here we begin transaction and commit transaction. In the transaction itself, we are going to have execute context function, which will insert the article. And the second part of it is we're going to insert an event into the outbox table. Insert event function can be reused by other methods, since it's probably very similar. You're going to have similar rows for different events. Now, if you take a look at this line, we also use defer rollback here. And defer rollback, first of all, defer will be called when function exits. And defer rollback can have two scenarios here. Let's take a look at the first one. In the first one, we exit with an error before we committed transaction. So something went wrong. We either couldn't insert an article, or we couldn't insert an event, which means that we can't make data atomic in this case. Or we could even fail to commit the transaction. In that case, so we also going to roll back. Defer will be called after we exit with an error, and then we will roll back the transaction. And the second scenario is when we exit at the very end. We exit without an error. We have committed the transaction at this point. Everything went well. we have inserted an article and inserted an event into the outbox. And what rollback is going to do in this case is it's not going to roll back the transaction, because transaction that has already been committed cannot be rolled back. So that's a nice way to work with this. Let's talk about an event relay. Event relay is an application we can build with Go, and it will forward events from the outbox table that stores events into our middleware. In this case, is an event stream. And with Postgres, we can utilize functionality that is offered by Postgres is for asynchronous notifications. So when there are some changes made in the outbox, new events appearing, we can listen to the notifications and process them. And roughly, there's the code that should give you a rough idea how it can work. So we can create a new database, we create a DB listener, and we start a Go routine that will be listening to new events from Postgres, and will be processing these events, forwarding them to event stream. Idempotency. It's important for operations to be idempotent in event-driven systems. What does it mean? It means when we perform an operation multiple times, it will not cause different result after performing it more than once, right? And one way we can solve this is to pass version number in our data structures. So when subscriber receives a data structure, it will be able to see the version and compare it against the version that it currently holds. And this will allow to identify the events that were older version, that were already processed. And if it's the same version that it already has, then the subscriber will know that we have already processed that version. So it can decide what to do. We can code that logic if we want to just discard these events. Message size. When we use middleware, they often put restrictions on how large we can use the message. So I already mentioned that we use Kafka, and in Kafka, the size limit is 1 megabyte. So because it's quite restrictive for us, we pass larger data size. So we use protobuf, and you can see comparison in a JSON structure. In JSON structure, you have the field name and the value, and in protobuf, is actually going to be an encoded binary, but to give you an idea, the data it will have is only going to carry values without fields. And after that, it will also do some magic to make sure that it is even less in size. So for protobuf, we also need to maintain schema. So publishers need to know how to encode the message, and subscribers will need to know how to decode that message. So schema, it's a very simple example. It does get a lot more complicated, and you can do a lot more cool things with protobuf, but to give you a basic idea how it works. So let's summarize. We talked about event-driven systems, that they use a synchronous way of communication. We learned that we can leverage asynchronous communication to make important parts of the system to be more responsive, to have our users have faster responses, improving their experience that way. We also discussed that event-driven systems are loosely coupled, so publishers, they don't know about their subscribers. We can have as many subscribers, and even subscribers can publish to the same topics, to the same event stream. So that makes event-driven systems very scalable and flexible. We've also discussed transactional outbox pattern. Main advantage of using it is to ensure data integrity. It may not be important in your system, but in our system, it is critical to have all of the events propagated to all other systems, and that improves our fault tolerance. And finally, it is time for some Q&A, and my colleague will assist me.
Hi, thank you very much. Yeah, my team is actually migrating to an event-driven architecture, so this is very useful. I took some pictures, thank you. I'm wondering, have you ever worked as a consumer of events? And if so, have you ever thought about having an inbox that, like, you know, records incoming events before you start processing them?
That's an interesting question. I've definitely been a consumer of events in my systems that I've built. But have not made an inbox before. But it's an interesting idea to explore.
Okay, thank you very much, Victoria.